Alrighty. Alrighty, good morning, everybody. Where is my stylus? There it is. Get started, shall we?
Get started, shall we?
Get started, shall we?
Get started, shall we?
We're gonna start.
We're gonna
So this in our book is chapter 5. So we can go ahead and get started, shall we? So thermochemistry, the beatboxing. Hold up, let me see. That should fix it now. Yes? Are we good, Michaela? For whatever reason, it activated my desktop audio. Okay, cool. Glad. Yes, because that's no good. I don't want it going crazy on you guys. So, um, alrighty. So let's do this then. So with thermochemistry, we're interested now in looking at energy of reactions. So previously, we have looked at matter transformations. And so we were looking at, chemical reactions, right? We looked at, silver nitrate plus copper turns into copper nitrate, copper 2 nitrate, rather, and silver, right? We looked at how matter was transforming, how it was going from different oxidation states or whatever different compositions of ions. That's what we had looked at in the last two chapters. But now we are going to look at energy. So, because we know chemistry is a study of matter, but matter and energy are intertwined, right? So, we do spend a good deal talking about energy as well. So, let's just this up. So, one thing we should note to kind of start off with is just like we studied with matter, remember that matter cannot be created or destroyed. We're going to see the same thing is true for energy. First thing to start off with energy cannot be created or destroyed either. It can only be transferred or transformed. So we can't destroy it or create it, but we can give energy to something else or take energy from something else. That's transfer of energy. Or we can transform it. We can use it for different types of energy. Typically, we're looking at heat and work as we do chemistry related things. And so those are kind of the energies we're looking at. And if we were to kind of define energy, remember we talked about kinetic energy and potential energy. Mostly we're talking about potential energy, so the energy that could be used to do things. So we're going to see that when we start talking about energy, it's a good idea to define kind of the units we're going to be working with. If we think about kinetic energy and go to physics for just a second, this is not an equation you're going to need, but this is how we can talk about kinetic energy. It's related to the momentum and the speed, right? So half mv squared is how we can talk about energy. And so the units for that, this is the important part. Units for mass would be kilogram, and V would be meters per second. So these are um, standard units we have. And so kinetic energy takes the units of kilogram meters squared per second squared, and we instead call that a joule. And so a joule is defined as a kilogram meter squared per second squared, for whatever that means to you. You can consider it, just for context, it's the amount of energy that a 2 kilogram object would have if it's moving 1 meter per second. It's not a lot of energy. And so very often we're going to have kilojoules, megajoules, gigajoules, bigger units. We typically have bigger units that we use for these. Just like we do with mass, like kilogram, megagram, that sort of thing. Um, and so this is kind of our standard unit of energy, which is the joule. We have another one called the calorie, which is equal to 4.184 joules. This is something you'll want to know, this conversion. Um, it was previously defined as 1 calorie was the amount of heat necessary to change the temperature of 1 gram of water by 1 degree Celsius. And that happens to also be 4.184 joules, and so they just sync them up. So this is not the calorie that you see on your. Let's see what I have that has calories here. I have nothing. So I'm in an empty house right now, so I have no calories apparently. But the calories that we see on nutrition labels are calories with a capital C, which is equal to 1 kilocalorie, chemistry wise, or 1,000 calories. So this is what you'll see on nutrition labels, and this is in terms of chemistry. So they are the same kind of unit, but it really means kcal, so kilocalories. In some places actually do say kcals, and in Europe they actually use kilojoules to talk about the kind of energy content of food. And so we'll use both of these units. We'll use joules and calories. They're both standard units for us. So we will be talking about them. Another conversion you'll want to know, I'm just going to put it out here now because we're going to talk about it soon. Um, there's another unit we're going to encounter called the liter atmosphere, because we're going to be talking about how pressure and volume uh, can do can be ways that we can kind of use energy as work. And so unit we're going to get there is liter atmosphere. Those that's a volume and a pressure unit. And so you'll also want to have this conversion in mind. So I would write these down for sure somewhere. These would be important ones to focus on, because your homework is going to be giving you things with liter atmospheres, and you're going to want to be able to convert those to joules and to calories and all that. So cool. Okay, so you'll want to be familiar with those conversion factors. All right, so that's kind of our units that we're going to be using with energy, um, and as a result, we can talk about many different things with this. When we talk about energy, we really mean a change in energy. It's very hard for us to define a 0 point for energy, Um, and since we can't say, okay, well, this thing has no energy, that's pretty much impossible, right? Because you'll have gravitational energy, electrostatic energy, whatever, some sort of energy is there. And so we really are talking about a change in energy. So we're exploring how things are gaining or losing energy, but we can't just say, it goes from this energy to this energy or something, um, because we don't really have those values, because we don't really have a zero. Without a zero, we can't say, okay, I have 15 joules, and now I'm going to go to 20 joules or something. I can say I've gained 5 joules, that's not a problem, but it's very hard for me to stick a number onto something with there's so many different types of energy that things are dealing with all the time. So really what we are talking about is a change in energy. And the letter that we used for that is delta E. Delta in chemistry always means change in. So a change in energy. That's really what we're talking about here. So we're looking at how much energy is gained, how much energy is lost, but that's a change in energy. So that's what we're going to be focusing on here. And technically, that's defined as your final energy minus your initial energy. But again, because those are very hard for us to define, very hard to put numbers for states of energy, we typically refer to things as the change in energy. All right, and so we'll see how to actually take this into terms that we're more familiar with, ones that are particular to chemistry, because we don't really talk about gravitation and, well, we do talk about electrostatics, but not gravitation very much. That's more physics, but yeah. Um, and so we might be describing energy graphically as well. We might say that I have some water, and we might describe what kind of energy is necessary to make things happen graphically. We call these energy diagrams. And so you tell me, if I want water at 25 degrees Celsius to become water at 100 degrees Celsius, do I need to give it energy? Do I need to heat it up? Or do I need to take away its energy? Do I need it to cool down? You tell me. What do we need to do to get this water to heat up? I guess I just said it, but if I want my water to get hotter, what do I got to do to it? Perhaps I should heat it up, yes? If I want my water to go from 25 to 100 degrees Celsius, I need to add heat, right? Absolutely. So that is absolutely correct. We need to add heat to it. If we want to go from 25 to 100, we add heat. Um, we're going to see that that's going to be a certain amount of energy. We're going to have to give it a certain amount of energy. And as you're absolutely correct in stating, you need to add heat to it. And so we will describe this process as endothermic. Heat must be added. If we want this thing to happen, we need to add heat to it. We got to put that water on the stove or in the microwave or whatever in the kettle. We have to give it energy somehow. And so we're going to see that this delta energy would be positive. We are increasing our energy. Our arrow is going up in the diagram. If I had water at 100 degrees Celsius, we would see that this one, the cooling process, would be exothermic, which means that heat is released. And we would see in this case, our delta E would be negative. We're losing energy. If we're cooling down from boiling to 25 degrees room temperature, we're losing heat. We're losing energy. And so we will put a negative sign there. We're going to see that typically we use other letters to describe these, but delta E is fine for now. So are we cool with these definitions, endo and exothermic? So in endothermic process, you have to add heat to get it to happen. If you're adding heat to it, it's going to have more energy, right? You're giving it heat, you're giving it energy. If it's cooling down, it's giving off heat. It's giving that heat to something else. It itself is cooling down. It is therefore losing some energy as it happens. And so we really see that in chemistry, energy kind of comes in two major flavors, we'll say. We have work and we have heat. Those are the main kind of forms of energy that we're going to be dealing with in chemistry. And very often, heat is going to be the most common. We'll see work is important, especially for those of you who maybe are going into engineering. Um, you'll be dealing with work a lot more, though heat is always still important. Um, let's talk about work, and then we'll talk about heat. In physics, work is the product of a force and a distance. So it's the amount of energy required to exert a certain force to move something a certain distance. It's something that we're not going to deal with in chemistry. We don't need this definition, but I'm showing you what work means. This is the important, or these are the important parts. There's a force component and there's a distance component. So something is being moved. That's the point here. So when we're talking about work in chemistry, something has to be moving. And we have quite a few examples of work in chemistry. This could be, for example, expanding a balloon, making a balloon bigger by adding gas to it or something. That's work that's being done. By making a balloon expand, you're moving the balloon. A piston in your car engine is moving up and down as gases are being burned inside of it. That's absolutely something being moved, and we know that that's a very important, everyday life thing where we're using chemistry, chemical reactions to do work to get our car to move from A to B. Although now, more and more electric ones are coming out, but that's a different type of thing. They're using electrical energy instead of chemical energy. Um, More examples, if you open a bottle of champagne, that cork launches halfway across the room and hits your friend in the eye, right? After you open the bottle after your first exam. And your friend will probably know that cork was moving, struck them, right? And so that kinetic energy of the cork moving that came from this work being done by the carbon dioxide in the champagne has now bruised them or something. So uh, we see that in chemistry. It's all about work is all about motion. So we have to consider whether something is being moved or not, and we'll see cases of that later. Um, in chemistry, specifically, most work is what's called pressure volume work. You know what? Actually, I want to talk about this in a little bit. I'm going to move this down. I want to first talk about how energy relates to work and heat. Heat is something we're going to focus on in a little bit. That is given the letter Q because why not? So Q means heat for us, and W means work. At least one of them has the right letter, right? So um, when we're talking about energy changes, delta E, change in energy, we're looking at, because in chemistry most things are a combination or just one of these, work and heat, um, we can define the change in energy as kind of some heat that's being either added or lost, and work that's being added or lost. And we're going to see that when we're talking about this, because heat is never created or destroyed, it's only transferred away or transformed into a different type. We need to define a few more things. But we're going to see that we have, okay, this is going away, way down. We're going to have a system that we're looking at, and we're going to have its surroundings. The system is whatever we're focusing on. We define what our system is. This could be a chemical reaction. This could be an object. It could be a car engine, whatever. Something that we are focusing on. We are defining our system. Typically, this will be a chemical reaction. We're in chemistry, right? The surroundings is going to be everything else. So if we're looking at my coffee cup, the coffee inside is my system. I'm saying that. Everything else, the coffee cup, the air around it, that's the surroundings. And so as my coffee sits on my desk, energy from the coffee is going from the system, its heat is going off into the air around it. The energy is being transferred, in this case, from the system to the surroundings. And so we're going to see that all these processes are always about transferring energy between these two things, whatever we're looking at. So if we're looking at a chemical reaction, if it's going to be losing heat, that heat is going to be gained by the surroundings. If it's going to need heat to um, absorb, then the surroundings will lose heat. And so if we think about the pot on the stove, here's our pot on the stove. I'm going to draw a very good drawing here. Okay, here's our fire. We have the whoosh, blue methane fire. Here's our pot on the stove. It's full of water, which is also the same color as the methane. Here we go. Okay, you know what? I don't like the methane. We're going to make it like whoosh fire. Okay, so here's our boiling pot of water. We're interested in the water. Let's say the water is our system. And we want our system to gain energy, right? We want to heat that water up. The surroundings would be the pot, the air, everything else, everything nearby. That's the surroundings. And so, in order to get our system to gain energy, we're going to use a different system. We have a combustion reaction taking place below it, right? That we are using to give energy to the surroundings. We're using a fire, this separate system, to give energy to the pot or to the air around it, technically. We're heating up the air, that air heats up the pot, and then the pot heats up our water. And so we're seeing there's in that case quite a few systems, and you know it's all about transferring from one to another. So if we're looking at the fire, it heats up the air. So the air is the surroundings for the fire. If we now look at the air, the surroundings for the air would be the pot and the everything nearby it, right? And then if we look at the pot, the air is the surroundings for the pot, as is the water, I suppose. And then if we look at the water, its surrounding is everything else. So it just, whatever we're looking at, that's our system. If we're looking at the system of water and we consider everything else our surroundings, if we want our water to gain energy, we need to have extra energy around it in the system, in the surroundings, so that the water can absorb it. So if we want our system to heat up, a good thing to do might be to heat up the surroundings. If we heat up the surroundings, we can therefore cause our system to gain energy. Because heat will kind of, what's the best way to phrase this? Will kind of, I don't want to say travel, but heat is transferred from whatever has high heat to low heat. So if you touch that boiling pot of water, you have lower heat than the water does. And so as soon as you touch it, that heat starts transferring into your hand. Your body senses that as extra energy being delivered to it and says, I don't want that. And your reflex, your hand gets yanked away, right? Because your body does not want this extra energy. Extra energy is a bad thing in terms of heat. So it's all about this kind of heat transfer, and heat will always go from high heat to low heat. And so it just kind of works out that way. So just like if you touch something cold, if you touch ice, if you grab a cube of ice, what happens to it? You feel cold, right? But cold is really the absence of heat. And so what you're really feeling is your heat going away into the ice cube. And you then notice the ice cube starts to melt, right? That heat energy is then being used to melt the ice. So there's all sorts of different kind of transferences of energy that happen all the time for us. Sweating is a very big, important one as humans that we need. And that's an energy transfer as well. How we cool our bodies off, because we don't want too high of heat. We also don't want too little heat, so we are very sensitive to our thermochemistry. So, anyways, that was a little rambling, wasn't it? But let's talk about this Q and W idea. With these ideas, we typically want to talk about signs of them. You can see that delta E can be, it can be negative or positive, right? We can lose energy or gain energy. And as a result, Q and W can also be negative or positive. And so it's hard to say I have negative heat or I have negative work, right? It's verbally very strange. But the signs of these things are going to kind of tell us the direction of where the energy is going. And so, oh my gosh, I should just erase this. I keep having to move it down. When we're talking about the sign of these things, if we're looking at when things are positive or negative, we can look at all of these things. If we're looking at energy, if we're looking at work, if we're looking at heat. So E, W, and Q. A positive delta E means energy is added to the system. So we're giving energy to our system. That's indicated by a positive sign. So the sign of our energy in our work, in our heat, is all about where the energy is going. If we have a negative energy, that's energy lost by the system. Again, we always kind of frame this conversation in focusing on our system. So if we're heating up our pot of water, we're giving it energy, we're going to have a positive delta E. If we're cooling off our water, we're losing energy, we're going to have a negative delta E for that process. For work, that is work done to the system. If you want to give something work energy, that could be like, I'm going to exert some work to move this box of binders up against gravity. I'm doing work on this system. This system, because it's out of my camera, but this system here now has more energy than it did when it was down here. So I'm doing work to this system. I'm moving it against gravity. I have to work to do that. And now it has extra energy, which I can then use to drop it. I gave it extra energy, and it then just lost its energy. So if the binder clip box was my system, I just did work to it to lift it up. And as a result, I lost the work energy. I had to expend energy. I had to give it the energy, so I lost the energy. And so that's what that means. Negative would be work done by the system. So if the system is being used to do work, that energy is going into something else. And so as a result, it's negative. So me, if I'm the system now, I am doing work to lift this up. Therefore, I have lost energy. The same delta E would be negative for this. I lost energy because I did work. I moved this thing up. The surroundings now, this dude, it now has higher energy. The surroundings is always the opposite of our system. So if I lose energy as the system, that means the surroundings has gained it. So if I lose energy by doing work, my sign is negative. That means I did work, the system gained energy. So system is always the opposite of whatever the system. Surroundings is always the opposite of the system. Um, and then with heat, it's heat added to system or heat lost by system. Coffee cooling down is negative. It's losing heat. That heat is going into the air around it. The air inside is slightly warmer than the air out here. We can tell that that air has gained some heat from my system. So therefore my system has lost heat. So this would be a negative Q. So it's all about how this is working. And what I think the book does a cool little analogy here is if you just consider like this in terms of money, um, all these positive ones, you can just replace the word like money, right? If if someone just gives you money, you now have more money. Yes, you will have a positive cash flow, you could say. Or same with energy and heat, we can say are kind of interchangeable here. So you're just giving money. Or if someone does work for you, like they remodel your house, let's say they do that for free because they're crazy, you will now have more money as well, right? If someone does work for you and you don't pay them because you're terrible. But that's all like adding to your bank account, right? Someone gives you money, or if someone does work for you, that's all kind of contributing. But if you give away money, or if you pay someone to do something, you're losing money, right? And so that would be the negative sign for all those things. So you have a negative cash flow if you're giving away money, right? So it's kind of the same way. So just look at your bank account. You have all these ways of putting money in. You have all these ways of taking money out. Same with heat and work. So if you are using your energy to do work, you're losing energy. If you're using your energy to heat something up, you're losing energy. So ponder that. So take like a few seconds and just kind of work through that here, because we're going to see the sign is definitely something important as we go through. Alrighty. Where's the example I wanted to do with this? Here in my notes somewhere. Oh yes, we're going to start talking about pressure volume work. Okay, we're finally ready to talk about pressure volume work. Oh no. All right. So typically, when we look at a reaction, let's say, let's take our vinegar and baking soda. I need to put the other one. Here's the reaction. Double displacement reaction we've seen before. We're going to see that when gases are involved, just an example, they can be utilized to do work. We could have this reaction happening. Oh, this is terrible. Let me do it thinner. We'll do it in a volumetric class for some reason. If we stick a balloon on this thing, that's an ugly balloon, but it's empty right now. If we add in our, if we do our reaction now, and we can add all that CO2 up into the balloon and cause it to expand, right? We can cause that balloon to grow, right? If we were to put, a balloon on top of this reaction, all those gas bubbles would fill up the balloon, right? That's how it would work. Um, as a result, that's work that's being done. An expansion of a volume is work. You can see that because we're causing something to move. We're causing this balloon to move. That's motion. Remember that work is all about something being moved. Or we say a piston. So here's our fun piston. This is in our car engine. Kaboom, we do our reaction here. And now our piston is up here. Really ugly arrow. Let's fix that. Oh my gosh, you're kidding me. I destroyed the wall of the piston. That's not good. Do we see here that these have different volumes? One has a larger space than the other. We have expanded this system, and by moving that piston up, we have increased the volume of, uh, of whatever we've done. And the way we've done that is by applying pressure to it. So if you want something to move, easiest way to do it is to add pressure to it. This is something that gases can do, but we can do it too. Pressure is a force exerted on an area, but if I want something to move, I just have to push on it, right? That's putting pressure. And so the gases, if they want that piston to move, they are putting pressure on that piston. And the more gas molecules that they have in that smaller space, or the more energy they have, they can push on it more. And so we see that the other kind of side of this is pressure, specifically related to gases. And so we see that work is going to be also defined as a change in volume, delta V, and the pressure associated with that change in volume. And we put a negative sign in there to help us understand what's happening with the work. If we cause something to expand, if something expands, making it bigger, that means that volume 2 is greater than volume 1, right? If something gets bigger, then that means the second volume is bigger than the first one, so it's bigger. That means, which since delta V would be our final volume minus the initial volume, or we can say 2 minus 1, we would have a positive volume change, right? So if V2 is bigger, that means if we subtract them, that will have a positive answer. So if this is positive, pressure must always be positive or zero, by the way. We cannot ever have a negative pressure. This one must be greater or equal to zero. So that means that if the change in volume is positive, we've expanded something, that means the work is negative. So if we have expanded something, that means our work sign is negative. And let's go ahead and see what that meant again. What the heck does it mean when work is negative? Oh, that means the system has done work to something. So we have caused that piston to move. We did work on that piston, thereby moving it, causing it to expand. And so we indicate that negative sign there to indicate that the work is being done by the system. Right? So we see that when you are expanding something, you have to do work to it to get that to happen. And so the work would be negative if your change in volume is positive, if you have a bigger thing at the end of your process. So producing a gas, making your balloon bigger, that means your system is doing work. And we can go ahead and do the calculation. Let's do it. Let's see. I've got one around here somewhere. Um, ba, 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 ba. 1 second, let me find it. Forget it. We'll just do it. Okay, let's say I can be as organized as I want, but then I never follow through with it. Isn't that always how it works? Let's say a piston um, causing the volume of 1.2 liters to increase to 2.6 liters. Um, is some random question. Okay, so we're saying a piston is moving, which is causing the volume to increase, and we have a pressure for it. If we want to calculate this work, let's calculate it in joules. The work done by the system in joules. So, formula. Work is negative pressure times the change in volume. Atmospheres is our most common pressure unit. That's something we'll focus on more when we talk about gases in a few chapters. But for right now, we're just going to accept that as a unit. So atmosphere, ATM, is a pressure unit. Even if you don't know that, you should know that liters is a volume unit, right? These are volumes. And we've seen that it's increasing, so the second one is our V2, our second volume, our final volume. And so, if we're to do this, we'll say, okay, well, we have negative 2.6 atmospheres times 2.6 liters minus 1.2 liters. And I don't have my calculator with me, so I'm going to do it on Google, and of course the mouse is not behaving. There we go. Do it. So 2.26 times 1.4. We do this, we get negative 3.164 liters times atmospheres. Don't forget your units. We're not done. This should really only be 3 sig figs, right? This is 1.40, which is 3 sig figs. 2.26, 3 sig figs. Therefore, our answer will have 3 sig figs when we're done with it. But we need to continue on because I asked for it in joules. And this is in liter atmospheres. So we've got to scroll all the way up to remember that I did give you a conversion factor way back when. We have 101.325 joules is how we'll convert that. So I'm going to just write that again down on our problem. It's 101.325 joule, or no, that is right, joules equals 1 liter atmosphere. We can go ahead and do that. So negative 3.164 liters times atmospheres. Put liters atmospheres on the bottom, joules on top. 101.325. I guess I put 326, but whatever, it's close enough. We get 320, sorry, negative 320.5954, we'll say. Still, we need our 3 sig figs for this, so we're going to round this to negative 321 joules. Again, it's negative because the system is doing work to expand that piston. To move that piston up against gravity is work being done by the system. So that is our answer here. So that's the work done by the system is 321 joules of energy to do such an expansion of volume. Fun. Fun, fun, fun. All right. It's always nice to do math, right? All right. Well, if we want to investigate things more, it'll be important for us to understand that when we're doing these sort of heat transfer ideas or work ideas, energy ideas, um, when we look at these, it's important to note that energy, the E, is what is called a state function. And this means that it's kind of constant for a set of conditions. But what does that mean? More importantly, is the second part, which just says the same thing in a simpler way to understand. It does not depend on the path taken to reach it. Let me give you an example of a state function that you'll be able to understand. So I had a friend who was flying from New York to Chicago a couple months ago, and she uh, could take a direct flight, go New York to Chicago. She could have a layover in Florida, which makes no sense, right? Go all the way down to Florida to then go all the way back up to Chicago. Or she could have gone to, I think, like Minneapolis or something, and then to Chicago. Those are three different paths that she could have taken to get from New York to Chicago, right? And no matter which one she took, she would still end up where she needed to be, right? The state function here is that the distance from New York to Chicago does not change in any of those. So she will still have traveled overall, I don't know how many miles, 1,000 miles maybe from New York to Chicago. I have no idea. Um, but whatever that distance is from New York to Chicago, she will only have effectively traveled that far, right? She might take this crazy path going to Florida, going all the way down to Florida, and then going to Chicago. She could go to Minneapolis and then to Chicago, or she could fly directly there. In either case, she's still effectively going the same displacement. So she is going from point A to point B. That distance is still the same. The distance between New York and Chicago is fixed. That is a state function. It does not matter on what path you take to get there. If you walk over some mountains to get there, that still doesn't change the lateral distance between the two cities. So that's a state function. That's what a state function means. It means it does not depend on the path. In chemistry, we can also define it in ways that are more a little, easier for us to understand. If I take out a bottle of water from the fridge, it warms up to room temperature, right? If I have my coffee and I let it sit here for 5 hours, it will cool down to room temperature, right? Doesn't matter if that thing was hotter to begin with or colder to begin with, eventually it will reach room temperature. And that means that the amount of energy at room temperature is a state function because that room temperature is the same. No matter if I started something hot or something cold, they both reach that same temperature, the same amount of energy. And so energy is going to be a state function. All right, so that's what I mean by state function. It is constant for a given set of conditions. At 25 degrees Celsius, my coffee and my bottle of water have the same energy. Thermal energy, I suppose, but that's what it means. All right, is that kind of clear? What's interesting, though, is that work and heat are not state functions. they do depend on how you do something. If I raise my piston way too high, okay, let's say my goal is to get this box of binder clips up to here, right? This is a fixed energy, this is a fixed energy. If I go crazy like this, the box has now this level of energy. It does not matter how crazy I went to get here, right? But in terms of work, if I go past this level and then drop it down again, I've done extra work. I've done more work than it would have just taken to do this, right? I did work here and then gravity took away some work there, but the amount of work that I did as the system can vary depending on whatever pathway I take. If I go like this, I do more work to end here than if I just lifted it up. Do we see that? Does that make sense? How work and heat do depend on the pathway you take to get to your wherever you're going. So I can put in a ton of work that is extra to get to where I need to go. It's not a state function. So just again, some vocab here, getting some thoughts in your head about how these things are going to work. All right. So fun stuff. Fun stuff. Let's talk now about another state function, another measure that we use, um, which is called enthalpy. Enthalpy, which is abbreviated H, let's see what would be a good way to describe this. Um, it is all about heat transfer. So all this energy we're talking about with work and energy, that energy has both. Delta E has both work and heat components. Enthalpy is just kind of heat transfer only. So we're going to see that energy, which had both work and heat as part of its definition, enthalpy is abbreviated with capital H. Often we put a delta with it because, again, we don't have a fixed enthalpy level. This is only about heat transfer. And we can describe it, oops, by kind of the change in energy plus any kind of work that's being done by the system. Because remember that work is negative P delta V. We're kind of getting rid of the work term out of this. So that's how we're going to do it. And so if we kind of relook at a couple of things, if you remember that delta E is Q plus W, and W is negative P delta V, if we substitute this in, we see that we're going to get Q plus W plus P delta V. And if we substitute W in, just substituting some things here, algebra, we get Q. This is the case at constant pressure. which is when we're going to be doing all of our chemistry anyway. All the stuff we deal with in this class is going to be done at constant pressure, um, mostly, I suppose. We will have cases where we don't, but at constant pressure, this equality is true. That delta H enthalpy is equal to the heat energy. That's it. That's it. It's going to be a quantity we use to relate something that's more theoretical, and this is something measurable. And we're going to see that if the work is done, that means if our pressure volume work doesn't happen, then delta H is approximately equal to delta E. I know we just did 15 different equations, but this is the point here. We're going to see that as a result, delta E is approximately equal to delta H, which is equal to the heat at constant pressure. And so, as a result, delta E not something we can measure, delta H not something we can measure, but Q we can measure. We can absolutely detect heat energy. Often we do this using temperature. We can relate temperature to heat energy. And so this allows us to go from something, again, this is theoretical. This is something measurable, or at least calculatable. And this is what we are interested in. So if we want to see how the energy of something is changing at most processes at constant pressure, which is things open to the atmosphere, we can measure that. That's the whole point of this. We're going to be able to see here that if we have a way of calculating Q, which we can do, we can get delta H. And if we can get delta H, we can say that's approximately equal to delta E. Change in energy, change in enthalpy. Thermodynamics is got a lot of concepts going on here. So it takes a little bit of processing time. So we're going to see here that we have many ways to talk about Q. We have many ways to talk about delta H, but we don't really have ways to talk about delta E, but that's really what we're interested in. We're looking at how energy is transformed over a reaction. We're going to do that using the other two instead. So very often when we talk about energies of reactions, we talk about delta H. That's something we can calculate theoretically, or we can measure it and calculate Q and set that equal to delta H. So we have multiple ways of looking at these things, and they all describe the internal energy of our system. So we'll let that sink in for another 15 seconds or so, and then we'll talk about this in a little bit more detail. That's what I want to do. All right. So we take a look at delta H a little bit more closely. We see again delta always means your final state or second state, whatever you're doing, whatever transformation you're doing, minus your initial state. That's what delta means, right? Delta means change in, which means you take your final value and subtract your initial value. In terms of how this comes to play in chemistry, we can say that as some matter transformation takes place, some chemical reaction takes place, there is an energy change. And so we can make this, because energy can't be created or destroyed, we can also say that this is the H of the products minus the enthalpy of the reactants. Our final state of heat, which will be the one that our products have, minus the initial heat, H enthalpy, heat energy, the initial heat energy of our reactants. So this is one way we're going to be able to describe it. We're going to learn later on that we have ways of taking a compound at a given set of conditions, because it's a state function. At a given set of conditions, each compound has its own delta, has its own H. And we're going to be able to use the idea that we can calculate delta H for a reaction by looking at the heat energy of the products and the heat energy of the reactants. I get this, by the way, that this is a lot of words, a lot of concepts. Take your time with this material. Pause the videos as you're watching these, because there's so much information here that may be difficult to kind of wrap your heads around. Pause the video, go do something for 10 minutes, come back, continue on. Like, give yourself time to really process this. This is one of the more difficult chapters that we deal with, because there's so much conceptual information as well as new kind of terminology and all that put in. So I would recommend doing that. Sorry for those of you who are watching it live, but sorry. You could always watch this later too. So, okay. Anyways, what was I saying? We're going to see that delta H, the sign of it, is important here. So if the product heat is greater than the reactant heat, then delta H will be positive. If we have the opposite case, delta H will be negative. We see that we already have terms for these processes. This one is exothermic. A negative delta H is an exothermic process, and a positive one is an endothermic process. And I'm going to represent this graphically for us, because that might help one of you perhaps. Actually, I'm going to go ahead and do this. As the reaction takes place, as we evaluate the reaction progressing over time, and if we look at our kind of energy as our y-axis, we kind of have two ways of looking at things. When we look at diagrams like these, I'm going to actually adjust this just a little bit. As we look at reaction progress and its relationship to energy, we see that right here is the energy of the reactants. And this is our energy of the products. Again, which is typically we represent by delta H, or by H, because we're talking about heat energy here. And so the difference in those two is your delta H for your process. And we see here that delta H is going to be, for this reaction, it's positive. Our products have higher energy than our reactants do. Our products are higher up on the y-axis. The y-axis is is our energy. So delta H is going to be positive for this. This graph represents an endothermic process. Our, our products have more heat energy than our reactants did. So that's endothermic. You see I have a hump in each of these. This is because reactions have things called activation energies. That's not something we necessarily have to deal with right now, but I don't want to just um, give you the start and the finish. Right? Thankfully, remember, delta H is a state function, just like delta E is. So it does not matter if we have whatever other pathway to get there. Maybe I have two different ways to get from reactants to products. I use a catalyst or I put it in an enzyme or something. Doesn't matter what the pathway is, it's just the state. I'm going to erase that because we don't need that here. If we look at this other one, again, our delta H is the difference between them. So delta H, and in this case, it's negative. We have a decrease as we go through. The product energy is lower than the reactant energy. So we take product minus reactant, we get a negative number. This is an exothermic process. This is just visually displaying what I wrote above. And the one on the left is endothermic. Intentionally pausing, by the way, letting this sink in for a second. But let's go ahead and move on. When we're looking at this, there's a couple things to note about enthalpy that we're going to want to consider. Delta H is a state function. It does not depend on the pathway you take to get there. From A to B, no matter what path you take, the difference is still the same. So, state function, okay? It's also an extensive property, which means it depends on the amount of matter reacting. So the opposite of this would be an intensive property, which would be something like density. A brick will have the same density whether you're looking at one brick or 5,000 bricks. They will still have the same mass to volume ratio. An extensive property depends on how much you have. So enthalpy will depend, especially when we're talking about reaction enthalpy, depends on how much matter you're reacting. If you put 1 mole of methane and burn it, you'll get out a certain amount of energy. If you put in 2 moles of methane and burn it, you'll get twice as much energy. And so the enthalpy is an extensive property. The amount of whatever you're doing to get your enthalpy does affect the number you get out. All right, and so often delta H takes units of kilojoules per mole. Kilojoules energy per mole of reactants or mole of products or mole of whatever. It depends on the amount of whatever you're doing. So if you're melting some water, melting some ice rather, uh, you the amount of energy required to melt that ice depends on how much ice you have, right? The amount of energy that you get from burning methane depends on how much methane you burn. The amount of energy you need to put into your water to get it to boil depends on how much water you want to boil, right? you know that boiling more water takes more energy. So we're going to see that's what we mean by extensive. So it depends on the amount of matter that you're doing something to. All right. The sign will change or reverse reactions or processes. And what we mean by that is if you say take, I'm just going to make up some numbers. If we say we take our reaction that we just wrote above, let's say the delta H associated with this process is, I'm going to just make up a number, I don't know what the number is, 200 and negative 202.1 kilojoules for this reaction. And it's exothermic. We know that because delta H is negative. If I just decide to arbitrarily reverse this, not going to happen, but if I decide to reverse this reaction, the amount of energy associated with this reaction, the number is the same, but the sign is different. So if you reverse your reaction or you reverse your process, you get the same number, but the opposite sign. So believe it or not, the amount of energy that you need to melt some ice is exactly the amount of energy you need to freeze that ice, freeze that water to make that ice. I mean, assuming you're dealing with the same quantity. So when you're looking at one process, if it's exothermic, the reverse process would be endothermic. And we might just say then that we can put these as parts of a reaction. For an exothermic for an exothermic process, heat is a product. So if I am going from this is an endothermic one, I guess I should have chosen a different one. Let's freeze some water. This is an exothermic process. It's an exothermic process because that water needs to lose heat energy in order to freeze. We have to take away its energy. We put it in the freezer. The freezer is very cold, so the energy is going to transfer out of the liquid water. That energy is going to leave, meaning it's exothermic, and we're going to get our ice. It's the opposite process for endothermic. Heat is a reactant. And so, if we want to melt our ice, endothermic ones are a little bit easier to visualize. We can do that. Notice these reactions are just the reverse of each other. So ice plus heat turns into liquid water. If I reverse that, liquid water can turn into ice plus heat. Delta H here would be whatever. I'm going to make up a number. Negative 80. Here it would be positive 80. Making up a number, but the point is the same. So it's important when we look at reactions, we're going to be talking about all these delta H things. And so when we're looking at diagrams. We can put this in diagram form as well. We can go from liquid water to solid water. We could lose some heat. Making up the number again. And I use purple for the endothermic, so we'll do that. The endothermic process, we would have to put in, give it 80 kilojoules of energy in order to get it to liquefy. This is what's called an enthalpy diagram. It's honestly the same as an energy diagram, but we're using delta H instead of delta E, even though they are approximately the same. So enthalpy is something we can calculate. We can get it from Q. We'll learn how to calculate Q next time. But we can figure out what delta H's numerical value is. Delta E, we are just going to approximate as delta H. So it's the same idea. Enthalpy diagram and energy diagram, the same kind of processes here. All right, so this is the idea of this part. So we've covered a lot of theoretical stuff today. It's going to definitely take some time because next time we're going to talk about calculating Q, and then we're going to do more like kind of theoretical how to calculate delta H theoretically. We're going to use just kind of either the compounds themselves or other reactions to figure out what delta H might be. We're going to do Q experimentally, as in we're going to use experimental data or an experimental process to figure out Q. Or we can also use delta H, which is calculated some other way. If someone's already done Q calculations for a particular reaction, we know the delta H of the reaction. We can use those delta H's to figure out new things. And we're going to see what that looks like next time. So, all the conceptual stuff today, we're going to deal with the math stuff more next time. So, prepare for that. All right. That's it for this week. I guess I can make your homework for this available, but I'm not going to make it due yet until we finish the chapter. So when someone inevitably posts in Discord, when is this homework due? There's no due date. Please tell them it's not due until I give a due date, right? So, which will be at least a week after when we finish the chapter. So just tell them that. All right, if you see that in Discord. So, alrighty. I think that's all I wanted to do. So, enjoy the rest of your day. Enjoy your weekends. Stay safe. Hopefully, the smoke will not kill you all. And yeah, we'll go from there. So, take care, everyone.